Okay, let's see, I'm here and I see two of you. We just wait one more minute. I think we're still lacking in class participation and students not showing up in class. So we have to find a way to encourage students to come to class. Do you have any great suggestions, Michael or David?
I don't.
Yeah, I don't really either. I think you're preaching to the choir.
Okay. Zheng Liu.
Hi, Professor.
You have any suggestion as to how we can encourage students to show up in class?
Maybe you can have like a quiz.
A quiz? An in-class quiz?
Uh-huh.
Yeah, the online students will complain that it's not fair for them because then they cannot take the quiz. So let's see how we can get started. Do you all have any questions today? I see Jason Johnson here. Okay. Jason, do you have any suggestion as to how we can increase class participation?
Maybe make your lecture notes not so useful. That's what
You
I
mean
think.
the lecture notes is better than the class lecture?
But I think that's probably what some people think is your lecture notes are so useful.
Okay. Well, I was thinking that when the weather gets warmer, which is actually about now, we can have a face-to-face meeting. I did that the semester before last, I believe, and we can meet in the Purdue Mall. And then maybe have some chat together, have a face-to-face meeting so that you won't miss seeing me in person. How about that?
Aren't most of the people who don't attend not on campus? Or is there's a
I think we have a number of on-campus students, but they're not showing up either.
Oh, I didn't realize that.
Are you all on campus or not?
I am.
Yeah, I am.
I'm
Okay,
also-
Michael, you are on campus or not?
Yes, I'm on campus.
What about Zheng Liu? Are you on campus?
No, I'm in California.
In California, okay. So if we have a face-to-face afternoon tea or something like that, you can join us. Okay, let's get started anyhow. I like to share my screen. Let me see how I can do that. I share my screen. And today I'm going to start on a very interesting topic and also a very important one, which is on radiation. Okay, on radiation by electromagnetic sources. Without radiation, we cannot have a lot of things that we have nowadays, which is wireless communication. Every one of us carries a cell phone. Our cell phone is actually talking to another cell phone through base station antenna towers and so on. And some of them are actually connected by satellites, low Earth orbit satellites and so on. So without this physics, we would not have all the conveniences that we have, that we are living with now. We find that wireless communication is so important. So I'll go through a brief history of radiation by a Hertzian dipole, and then talk about some approximations, near field, far field, radiation power directive, gain pattern, and radiation resistance. Okay, so here is a antenna tower. This antenna tower is coming from this station AM 920, and the frequency of this is 920 kilohertz. Okay, and the wavelength, I believe, is around 300 meters at this frequency. There's a simple rule of thumb that I used as a student when I was working in a microwave lab. I was always told this rule of thumb, 10 gigahertz. 10 gigahertz implies 3 centimeters, okay? Then 10 gigahertz is 10 to the 10 hertz. The wavelength is 3 centimeters. And then if you look at this station, is about 1 megahertz. Okay, 1 megahertz is 10 to the 6 hertz. So if you can compare these two frequencies, one of them is 10,000 times higher than the other frequency. Hence, if you go to 1 megahertz, then the wavelength should be 10,000 times longer. So you have 30,000 centimeters, and then it would be 300 meters. Okay, you can use this formula as a rule of thumb to work out wavelengths. You just have to remember one bit, which is this one, just using proportionality constants and scaling of wavelengths and so on to get wavelengths at one frequency. And then you can quickly figure things out. Okay, so Hertzian dipole is going to be what we want to talk about, because when you have a wavelength that is so long, a dipole, even though it's an antenna tower, which is not small, can be thought of as a short dipole. So this is a short dipole, which is approximately what we call a Hertzian dipole. Okay, it is approximately a Hertzian dipole because it is so much smaller than the wavelength that it is operating with. Okay, and Hertzian dipole was invented around 1888 or Heinrich. I think his name is Heinrich Hertz. Okay, he did an experiment in 1888 and proved that you can use a small dipole to radiate electromagnetic field. And you can imagine how slow progress things were. 1865 was the onset of Maxwell's equations. Okay, and then it was some 23 years later, if you subtract this two, it's 23 years later that people understood Maxwell's equations, what it was all about, and then started to work on experiments to verify Maxwell's equations. And the story was that when Maxwell's equations were first written down, very few people can read beyond the first 50 pages of treatise of electricity and magnetism. So James Clerk Maxwell wrote a book called The Treatise of Electricity and Magnetism. It was very hard to read. Okay, it was not until Oliver Heaviside, in English, an eccentric English genius, as some people like to refer to as, who took Maxwell's equations, which were some 20 of them, and rewrote them in the 4 Maxwell's equations that we see in textbooks these days. Okay, so knowledge progresses slowly throughout the ages. This is what we can learn from this historical story. But when a dipole is very short compared to wavelengths we can approximate it with a dipole such as this one. It can be thought of as consisting of two reservoirs at the end, okay, two charge reservoirs at two ends, and then you drive it with a generator. And at very low frequency, it's almost like if you have a transmission line, and if you connect it to a generator, you probably would know that how difficult it is to drive current into this transmission line because it is an open circuit. So one way to drive current into this transmission line is to put a capacitor at the end of this open circuit transmission line. If the capacitor is large, then you can have a current flow. Okay, you can have a current flow, AC current flow through this transmission line. The same idea is being applied by Hertz. What he did was that he used a sphere which is large enough so that there is a capacitive coupling. There is electric field that goes from this sphere to the other field. So you can think of them as having capacitive coupling between them. And because they have capacitive coupling, you can think of the equivalent circuit as something like this. Okay. So how did he drive this antenna? Well, he made two spheres which are relatively large compared to the size of the wire. His driving point was here. Okay, he knows that he needs large capacitive coupling between these two spheres in order to drive any currents into this antenna. And whenever you have some current traveling in the antenna, you can show later on by mathematics that this current, which is traveling back and forth, would radiate. And that is how Hertz did it. And this is how he drove his capacitors. He actually used a transformer and he used a battery to charge up the high voltage, and then he used a switch. And when you have a switch, you can cause a large voltage transfer by this transformer to set up the voltage, and this voltage drives the current into the capacitor. And he picked up the signal using a loop antenna, a current loop. The current loop will intercept the magnetic field generated by this antenna, and the magnetic field produces a force by Faraday's law or Lenz's law, produces a voltage at this gap, and he actually can detect electric sparking, the sparking of electric field at the voltage gap, indicating that, in fact, his receiver is picking up some electromagnetic signals. Okay. Are there any questions regarding this very interesting and historical experiments? Okay. If not, let's go and study some mathematics behind this. We're going to study the math that relates vector potential and scalar potential to the current sources. And we have learned that if you have a vector potential, we earlier have derived that vector potential has to satisfy this Helmholtz equation. And the current on the right-hand side is given by this factor, and this is the vector potential equation. Okay, and then in addition to that, we have the scalar potential, which satisfies this Helmholtz equation, but it is totally scalar. Okay, and then once we have found the vector potential, we would know how to find the magnetic field using this equation, because the vector potential is designed such that B equals to curl of A. Okay, and then the electric field can be found by using this equation that we have derived earlier. Electric field is related to the scalar potential and the vector potential in this manner. And we are going to approximate the current as a point source because the current is so small. Okay, you think of two spheres, and there's a current flowing in between these two spheres, and there's a plus Q here and a minus Q here. And then there's an I that flows in between these two spheres. And if you were to look at this current, it's three-dimensional, and we're going to approximate it with a small current that flows in a small part of space. And you can think of this as being approximately a current that looking like this. Okay, it's flowing in the z direction. This is a z-axis, and it has a current of amplitude I. And then you can show that the current moment is actually I times L, L being the separation of these two charge reservoir, and that you can approximate this current as delta X, delta Y, and then it's some function of Z. Okay, you can assume that this current is infinitely thin in the X direction, infinitely thin in the Y direction, but described by a box function in the Z direction. Eventually, you can say that the box function is so narrow, and it becomes a delta function as well. Okay, so this would be the approximation for our current. And also, I like to point out the fact that the dipole moment for this dipole is given by QL. Okay, and if you were to differentiate this dp dt, it would be equal to dq dt L, and dq dt L is going to be just current. If you have two charge reservoir that's changing with respect to time, it will cause a current flow, and this part has to be I, okay, by charge conservation. So this is IL. So what we have is that IL can also be written as J omega PL, J omega QL, okay, because I is equal to dq dt, which is J omega Q in the frequency domain, and hence you can say that this is just essentially J omega PL because P is a dipole moment. Okay, so alternatively, we can also write our current, if we choose to, as Z J omega QL or P delta X delta Y delta Z. Okay, this simplification allows us to find the solutions to these equations quite easily because they're extremely simple. Delta functions are something that electrical engineers love, okay, because you can do a lot of interesting things with it. And we have learned previously that once you have a current, you can solve that equation that we have there by using this formula, and it's given by mu, the convolution of, I'm not going to write the triple integral. It's just a volume integral. Okay, I'm going to denote it with the R prime, and it's understood that this is a volume integral. And it's the convolution of the current on the right-hand side with the Green's function. And the Green's function in this case is given by this. Okay, and that is the solution of the vector potential related to the current that we have in the system. But the current here, as we said before, is a point dipole. We make it a mathematical approximation and write this as delta of R. Okay, where this, if you were to write this out explicitly, it would be delta X, delta Y, delta Z. Okay, and this is just a shorthand notation for this. if you want to write a shorthand notation for that, you just use this notation. And now we can plug this in, put this in there, and put this in there, and noticing that the r prime is just a shorthand notation for the x prime, the y prime, the z prime, and you plug this in there and use the shifting property of delta function. Okay, if you use the shifting property of delta function, then after integration, this will just become, with its r prime value evaluated at the origin, at where r prime is equal to 0. And what you have then is that you have a closed form solution for the vector potential, and it's given by z is pointing in the z direction because of that. Okay, and then there's a mu somewhere, and then there's an IL coming from here, and then you will have e to the minus j beta r over 4 pi r. Okay, what happens is that r minus r prime becomes just magnitude of r, which is just equal to r, because r prime has to be set to 0 by using the shifting property of delta function. Okay, so wonderful. We have found the closed form solution of the field radiated by a Hertzian dipole. The next thing is to find the corresponding magnetic field and the electric field. Okay, so to find the corresponding magnetic field, we use the fact that, as I said before, mu h is curl of A over here, and then using that, we find that H is given by curl of A over mu. Okay, and then you would have to work this out. And you will have to work this out in cylindrical coordinate system, because this vector potential has cylindrical symmetry. It is axially symmetric. Okay, actually you can think of it as being spherically symmetric, but because of the z hat, it has axial symmetry. Okay, so this thing has axial symmetry. Or cylindrically symmetric. Okay, so it would be a lot better to write this out in cylindrical coordinate system. And then if you were to look up the table for curl, then it would be 1 over mu. Here is the table lookup part, which I'm not going to go in great detail, but that you will have this term, only 2 terms, and I explain to you why only 2 terms. Okay, and then you have another term that looks like this. The reason why you have only 2 terms is because we have to assume that partial phi equal to 0. Okay, you have to assume that partial phi equal to 0 because, let me see if I'm missing something. I don't think I'm missing anything. Partial phi equal to 0. So if you plug in the curl operator should actually have a rho term. Okay, I think the rho term is 1 over rho. Let me see. Partial rho plus phi 1 over phi partial phi. Plus something like rho phi z partial z. So you will have to take this curl with those components in there, and you find that you can assume that your A has only phi component. Sorry, your A only has z component. Okay, A has only z component. if you look at your A, it only has Z component. We are going to assume that A phi equal to 0 because A does not have the phi component. So if you were to work things out, you find that this term that is the only contributing term because partial phi equal to 0. Okay, so the only term that's left is this term crossing with this term if you work this out. And hence, you can work out the curl of A quite easily. And what you have is that you need to evaluate what partial rho A of Z is, and you already found what A sub Z is. A sub Z is this complicated mess over here. And then you will have to differentiate this with respect to rho, and it doesn't look easy for most of us. Okay, you plug this term AZ in there, and you get mu IL e to the minus j beta r over 4 pi r. Okay, so this is tricky, and it's tricky because most of us do not know how to differentiate expressions like this. I think most of you do, but a large number of us do not know how to do that. So what you need to do then is actually to write your R in terms of rho in Z. Okay, R is given to be that, and then you can differentiate. Okay, another way is actually to use the chain rule and say that partial rho is the same as I have written it down, is partial R, partial R, partial rho. Okay, and then you put this in here. You can use this chain rule and differentiate the expression first with respect to R, and then find partial R, partial rho. Okay, and then you can find partial R, partial rho by doing this, and you will find that this is actually equal to rho over rho squared plus Z squared if you go through using what you have learned in high school calculus. And if you do that, then you have what you need, and you can actually find out your H field. Okay, the H field, after you have plugged it in those things, you find that H has only a phi component. Okay, only this component survive, because if you take this cross product out, only this term crossing with Z survive, and rho crossing with Z give you phi, so you only have a phi hat term left. And if you work things out properly, then this is rho over R, IL over 4 pi R, minus 1 over R squared, minus j beta 1 over R, e to the minus j beta R. Okay, you're going to have this rather complicated expressions because of all derivatives that you need to do. And then you can find a closed form solution for E as well. The closed form solution for E can be gotten directly from the magnetic field. You can do it two ways, actually. You can choose to find the scalar potential and find the E using this formula. You can choose to find the electric field using that formula, or if you don't want to find the scalar potential phi, you can take the curl of this expression. Again, you do a table lookup on how to write curl in the cylindrical coordinate system when you only have a phi hat. And if you work this out, it's a rather laborious exercise, but it's not rocket science, but just a lot of laborious work. And if you work this out, it's going to be something that looks like this: 1 over j omega epsilon, and I can write down the answer for you, 1 over r sine theta. Actually, I can also write out this table lookup formula for you. If you do a table lookup, okay, you will have something like this because you only have h feet. Okay, and then you will have generating, you will only have a formula that has only r in theta component. So that is what your E should be, and then you do some cranking. Okay, plug this in there and crank. It's not rocket science, but I'm sure that all of you know how to do that if you have enough grit and if you have enough stamina. But these are all kind of 19th century mathematics. Okay, calculus was invented quite long ago. Okay, if you do this correctly and you have the grit to do it, then this is the expression that you get. And then you have a theta component times sine theta. And then you have to multiply by a term that looks like 1 plus j beta r minus beta square r square. Okay, and I'd like to remind you of what the spherical coordinate system is. That is, if you have a spherical coordinate system, you have x, y, z, and then you will have a theta, and then a phi, and then your observation point would be over there. Okay, and then you have to familiarize yourself with the spherical coordinate system again. Okay, are there any questions regarding the derivation of this formula? So these formulas are very, very complicated. They do not give us much physical insight if we just stare at them. So we like to stare at this formula in two regimes. That is, when we are very close to the dipole and when we are very far away from the dipole. Remember, these formulas are closed form formulas, so they are valid everywhere outside the source region. And we like to concentrate ourselves in two regions. Okay, one is in the far field. In the far field region, we assume that beta r is much, much larger than 1. Beta, remember, is 2 pi over lambda. So beta r is 2 pi r over lambda. So when r is very much larger than lambda, which means that we are many, many wavelengths away from the source region, then we can make approximations. Remember that beta r, I have written them together here, so that when beta r is large, you can keep only the large term. You will have a term here that is the largest. Okay, this term will be the largest, and then this term will be smaller than this term, and then this term is also small, and the one term is going to be very small. So you can see that when beta r is very, very large, this is a dominant term. And I would have the fact that electric field can be approximated by the dominant term. And if I write down the dominant term is this term over here, it has a theta head component multiplied by sine theta, keeping only this term. And then I will cancel some r squared with r cubed in the denominator. And after some simplification, I would see that electric field is primarily pointing in the theta head direction. And then I would have the rest of the term written to be something like this. Okay, 4 pi r e to the minus j beta r sine theta. Okay, so that is the far field. This is called the far field because we are very far away from the source term compared to wavelengths. The yardstick is the wavelength. So remember, in the electromagnetics, the yardstick we have is the wavelength. Okay, lambda is our yardstick. Okay, so then you can do the same with the magnetic field that we have derived. And when beta is very, very large, this term dominates. This term can be ignored. And then upon simplification, you have the fact that the magnetic field can also be approximated as phi hat beta IL. Beta IL because there is a beta that remains here. Okay. And then divided by 4 pi r e to the minus j beta r sine theta. Okay, where did the sine theta come from? Well, the sine theta come from rho. If you were to find the relationship between rho is the relationship, rho is in this direction, z is in this direction, theta is this angle, and if you remember your spherical coordinate system, rho, the distance out from the origin, rho equals to r, this is distance r sine theta. Okay, that distance is r sine theta in spherical coordinate system. And when you plug that in, you will get this sine theta. So this is the far field for a Hertzian dipole. And what is remarkable about this is that if you look at the ratio of these two fields, one of them is pointing in the theta directions. The other one is pointing in the phi direction. And I have to remind you what the theta direction is in the spherical coordinate system. If I were to draw it in this manner, theta is pointing in this direction. Okay. And what is the phi hat direction? That is a bit harder to draw. Again, I can draw a 3D picture of this. And if I were to draw the phi hat direction, it's something like this. So if I were to superpose on this picture, phi hat would be something like this. So if I were to superpose in this picture, okay, this is z-axis, phi hat is pointing into the paper. So one thing to notice is that the magnetic field is pointing in the phi hat direction due to this Hertzian dipole. I have a Hertzian dipole that is radiating at the origin. And it's producing a magnetic field that is pointing in the phi hat direction, but it is producing a electric field that is pointing in the theta hat direction. And which direction is this wave propagating? Okay, it's a spherical wave. So it is propagating in this direction. Okay, because it is a spherical wave. If you look at the physics of this wave, it is a wave that's emanating from the origin. So if you look at the relationship between EH and the direction of propagation, it looks like that of a plane wave. E cross H is equal to K. Okay, this is the beta vector. You'll find that E cross H is actually the same as the beta. Okay, there's one important thing that you should notice here. What other things that you should notice? Let me think. I'm missing a J here. Okay, if you go back and do it more carefully, there's a J here that I'm missing. So the two are in phase. That's important. Otherwise, the phase would be out of phase and then the wave is a little bit wacky. So in other words, they're in phase and they're orthogonal to each other. And what more, if you take the ratio of these two waves, if I take the magnitude of E over the magnitude of H, I will find that these two terms will cancel each other, and then I will have omega mu over beta. Okay, omega mu over beta. I cancel the two J's. They don't matter. The sine theta will cancel, and this is just omega mu epsilon. And if you see what this is just mu over epsilon. What is the square root of mu over epsilon? Something that you have learned before. What do you call that? Impedance. Impedance. Okay, this is the wave impedance. The the wave impedance of free space. So this wave actually behaves like a plane wave. Okay, and you can also look at the near field. I don't think we have time to look at the near field. Okay, but you can also take the other limit that you're very close to the source, and you will see that the near field makes the field looks like that of an electric dipole. I will let you do that on your own. I like to move on to a new topic. Do you have any question before I move on? I like to find the power radiated by this Hertzian dipole because power is very important for wireless communication. So I like to find the Poynting vector. The Poynting vector, complex Poynting vector is E cross H conjugate. Okay, and then you recall that the time average of the instantaneous Poynting vector is half, let me call this complex Poynting vector, is real part of the complex Poynting vector. Okay, the time average of the instantaneous Poynting vector is half the real part of the complex Poynting vector. And hence, I can say that time average Poynting vector is half real of E cross H conjugate. Okay, and now if you plug in this value of E that you have found and value of H that you have found, remember that their relationship are just like plane waves. And the time average Poynting vector should also be like that of the plane wave, except that it is pointing in the r hat direction, because one is in the theta direction, the other one is in the phi hat direction. And if you take theta crossing with phi, you get r hat. And then you will find that the rest of the term becomes like that of the plane wave. And you can actually write it more simply like this. And this is a plane wave relationship. In the beginning of the course, when we take the plane wave and find the time average Poynting vector by plane wave is given by that formula, except that you have to make sure that this thing is pointing in the r hat direction. So we can write this as r hat s of r if you want to. The time average of the r component of the instantaneous Poynting vector is equal to this formula over here. Okay, so one thing to notice is that this S is proportional to sine squared theta. Okay, that is one thing that you should notice, because you can one sine theta from here, one sine theta from here, and hence the thing is actually proportional to sine squared theta. Or another way to look at it is that the E field is proportional to sine theta. E squared would be proportional to sine squared theta. And if you were to look at this thing, okay, now you can use this formula to find the total power radiated by this Hudson dipole. And another thing to notice is that the radiation pattern, if I call this the X and the Z direction, the radiation pattern will look something like this, which is a plot of the magnitude of E. If I were to take the magnitude of E and plot it, this thing will be proportional to sine theta. Okay, it will be proportional to sine theta, and if you plot it out, it looks something like this. So when theta is equal to 0, it doesn't radiate in that direction. But when theta is 90 degrees, it radiates in the what we call the broadside direction. This direction is usually called broadside. Okay, and then you can also plot S. It will look a little bit squeezed like this because you square the function. Okay, this is sine squared theta. Okay, so it looks similar, but very much looking like this. And I'd like to just remind you of what the spherical coordinate system is. I actually have this plot over here. So you can see that this is phi, this is rho, and then this is phi hat. And there's also a unit vector that goes like this, and there's a unit vector that goes like that. And this point here will be r theta phi. R theta phi. And this is the position vector. R is given by that. Okay. And then you can see where phi hat is pointing. I should also like to point out that theta hat is pointing in that direction. Okay, and then z hat is of course pointing in those directions and so on. Okay, so let's get back to this radiation pattern again. And if I were to look at the power is equal to the integration of the pointing vector over all angle. Okay, so what I need to do then is to take this time average pointing vector, point it in the r hat direction, or find its r hat component, and then do a integration over all angles, and then do it over all the 4 pi radian. This d omega means angular integration. So this is actually r squared sine theta, d theta d phi, if you write that out explicitly. But usually in shorthand notation, you just write it as a d omega. And then you can find that this is sine squared theta. Okay, you already found that this is actually something looking like this. Okay, you can actually work this out as proportional to sine squared theta. So this is proportional to sine squared theta, and there's an r squared here that cancels the r squared that comes from this product. If you take E with H, you'll find that it produces an r squared, and that cancels this r squared exactly, and then this would be actually something that is independent of r. And if you do this carefully, I'm not going to do it for you, but it's done in the lecture notes. And it turns out that this can be written as 4/3 pi eta of the free space times beta IL over 4 pi squared. Okay, that would be given by this formula. You can actually prove that integration of sine cube theta, because there's a sine cube theta involved. There's sine theta from here, and there's the sine squared theta from your S. Okay, there's a sine cube theta. You can prove that the integration of sine cube theta from 0 to pi is equal to 4/3. It's proof in the lecture notes, so I wouldn't bother to prove it again. Okay, you can get radiation pattern, radiation power pattern, and hence you can define a lot of quantities. There's one other quantity that I like to define, which is called the gain pattern. The gain pattern is defined to be something that's the function of angle, and is given by the time average pointing vector in the r direction divided by the isotropic power density. You assume that this total power is being radiated isotropically, which means that equally in all directions. And this ratio of the actual pointing vector divided by something that is radiating isotropically, you find that this is a function of theta and phi, and then this is called the average pointing vector, because you equally distribute the vector, the power over all directions, and you can find that this can be worked out in closed form is given by this formula over here for Hertzian dipole. Okay, and D is something that is defined to be max of G theta phi. D is called the directivity. It's called the directivity. Okay, if you look at this function, and it makes at 3/2. Hence, the directivity of a Hertzian dipole is 1.5, which is not very high. You can actually engineer good antennas so that the directivity becomes high. For instance, if you were to put a Hertzian dipole in front of a reflector antenna, you can get the radiation pattern to look like this. And then the directivity of such an antenna could be a few hundreds, okay? And also there's a concept of a effective current. We have assumed the current to be a constant. On a short dipole, the current is actually not a constant. It has to vanish at the endpoints because there's no capacitor, there's no spheres there. So if you just have a short piece of wire, okay, if you have just a short piece of wire, and if you drive it with a voltage source at the center, the current is going to vanish at the two ends. The current looks more like this. And this is, in a sense, effectively equivalent to a dipole with a constant current with half its length. You put this to be A/4 minus A/4. And these two currents have the effective radiation power because the radiation power is proportional to the integration of this. Okay, and I can talk more about that later on. And actually the currents are never looking like this, and they more or less look like this on the dipole. It more like the current distribution on the transmission line, okay? Because of that, calculating the radiation power exactly is quite a difficult task. It's quite a difficult endeavor, but however, many researchers have worked that out for you. Are there any questions before I stop here? If not, I'll stop here and let you go then. Okay, I'll stop here and let you go. And see who is here. Okay, I'll let you go, and I'll see you next lecture then on Friday. Okay.
Thank you, Professor.
Okay, thank you for coming.
Thank you, Dr. Chu.
Thank you.